So in the past few videos, we've gone over a lot of information already, and I've tried to kind of give you that information, not just telling you the answers, but sort of explain why things are the way they are, which can be kind of confusing. I mean, hopefully that's the easiest way to learn it, but sometimes it's nice to just sort of ask the questions, see the answers, kind of get some practice rapid fire. That's what I'm going to do in this video. I'm going to give you an example, and in fact, it's an example we've seen before. F of x equals 1/3 x squared minus x minus 2. It's the exact same function we saw in the previous video. And this function is given to you both algebraically and geometrically, meaning you have the equation and the graph. And I'm going to ask you a bunch of questions, most of which I've already asked you, but some of which I haven't. And what I'm going to do is just answer all these questions without all kind of the fluff and description and stuff, just show you the quickest path to the answers. So without further ado, the first question, or the first group of questions, really should be review from a pre-calculus class, although I recognize that for some people it won't be. The first of these kind of review topics is to determine f of 3, and I want you to do it two different ways. I want you to do it completely algebraically and then completely geometrically. So what I'm saying is pretend you don't have this graph here at all. All you have is this equation. Could you figure out f of 3? And hopefully you're like, yeah, we did that in the previous video. In fact, with this exact same number. All I got to do is copy exactly what I see written here. Think about this as like the blueprint of the function, except change all the x's, the generic input, into 3's, the specific input in this case. So I'd get 1/3 times 3 squared minus 3 minus 2, which is a third of 9. In other words, 3 minus 3 minus 2, which is negative 2. Evaluate f of 3 algebraically. Here's how you do it. You get negative 2 as the answer. And as we've seen before, not only can we do this algebraically, we can also do it geometrically. Even if you didn't have this equation at all, as long as you had this graph, it would be maybe even easier to figure out f of 3. All you'd have to do is recognize that this 3 is playing the role of the input, the x. The input into the machine goes on the x-axis here. Here's where x equals 3 at this point right here on my graph. The output that corresponds with this point is negative 2. Therefore, because this point 3, negative 2 is on my graph, f of 3 is equal to negative 2. Easy enough, we can move on. What if the question was slightly different? Instead of evaluating f of 3, what if we were trying to solve f of x equals 4? The big difference between 1 and 2 here is in 1, you're told the input, the x value, whereas in 2, you're told the output, the f of x, or y value. The output for this machine is supposed to be 4. We want to figure out what input or inputs would lead to that output. Again, we can do it two different ways, algebraically or geometrically. If we were doing it algebraically, what we would do is say that the output to this function is 1/3 x squared minus x minus 2. And I want to figure out when that output is equal to positive 4, because I'm trying to solve when f of x equals 4, and f of x is this expression. Solving this equation for x will tell me what x is equal to. X is the input, which will be the answer to this question. So how do you solve this equation? Well, there's at least 3 different ways to solve this equation. The one that I think will be most useful to you in this class is to solve this by factoring. So the first comment is it only helps to factor when your equation is set equal to 0. So don't try to factor the left-hand side right here. It won't help you. First, subtract 4 from both sides of the equation to get 1/3 x squared minus x minus 6 equals 0. Now that your equation is set equal to 0, you can factor to solve. You can factor immediately in this form, but it's easier to factor when your leading coefficient, the number out in front of the x squared, is a 1. In this case, it's not a 1, it's a 1/3, but I can make it a 1 if I multiply both sides of the equation by 3. So if I multiply the right side of the equation by 3, 0 times 3 is just 0. If I multiply the left side of the equation by 3, 1/3 times 3 is just 1. So I get 1x squared. Negative 1 times 3 is negative 3. So I get negative 3x. And negative 6 times 3 is negative 18. So I get x squared minus 3x minus 18 equals 0. My equation set equal to 0, and the leading coefficient, the number in front of the x squared, is a 1. And that's going to make it as easy as possible to factor. If it factors in the form x plus or minus something times x plus or minus something. And those two somethings need to multiply to negative 18 and add to negative 3. So if you focus on what numbers multiply to give me 18, 1 times 18, 2 times 9, 3 times 6, yeah, that's all true. And if it's going to be negative, one of those has to be positive and one has to be negative. And of those pairs that I listed, the only one that will add to negative 3 is if I put negative 6 on one side and positive 3 on the other side. Note that 3 times negative 6 is negative 18, and 3 plus negative 6 is negative 3. So what that means is this line is equivalent to this line, but this line is preferable because in this line I got something times something equals 0, and there's this thing called the multiplicative property of 0 that tells me that only happens if one of these two things themselves are equal to 0. So either x plus 3 equals 0 or x minus 6 equals 0. I've changed this one hard equation, or maybe this one super hard equation, into these two really easy equations. Solving these, it's almost trivial. Subtract 3 from both sides, you get x equals negative 3. Add 6 to both sides, you get x equals positive 6. What we figured out is if x equals negative 3 or if x equals positive 6, what will come out of this machine is positive 4. So our solutions to solve f of x equals 4 algebraically is x equals negative 3 and x equals positive 6. We can do all that algebraically, but we can also do it geometrically. It's a little bit easier, I think, to do it geometrically. For doing it geometrically, we just have to recognize that this 4 is the output to the machine. The output doesn't go on the x-axis, it goes on the y-axis. So what I'm doing is I'm looking on my y-axis here and figuring out when the y-coordinate equals 4. Looks like that happens in two different spots. It happens over here when the x-coordinate is equal to 6, and it happens over here when the x-coordinate is equal to negative 3. Sure enough, 6 and negative 3 were the exact same answers we got before. We can solve this equation algebraically or geometrically and get the exact same answers. The next of the topics that are technically pre-calculus topics that I'd like you to be good at for this class is to sketch the secant line to this function. When you're thinking secant line, you're thinking, oh, that's the easier case, the line that's defined by two different points. So you better be told two different points. Sure enough, you are. The secant line from x equals 3 to x equals 6. A nice thing about x equals 3 and x equals 6 is those points are already labeled on my graph, right? Here's where x equals 3, and here's where x equals 6. So the secant line is just the line that connects those 2 points. Here it is in all its glory. You're asked to sketch the secant line. It's given in pink. We've now sketched the secant line to this function f from x equals 3 to x equals 6. With that secant line, we can do two different things. The first thing is to calculate the slope of that secant line. The nice thing about the slope of a secant line is it's pretty easy to figure out. As long as we have 2 points on the line, our equation for slope is it's the change in the y-coordinates divided by the change in the x-coordinates. So maybe I let 3 be x1 and 6 be x2, in which case the y value corresponding with 3, negative 2, would be y1, and the y value corresponding with 6, in other words positive 4, would be y2. I throw all those numbers into this formula, and I get 4 minus negative 2 divided by 6 minus 3, which is 6 divided by 3, in other words 2. The slope of the secant line is exactly 2, as we can verify by looking at the graph. We had already calculated the slope of the secant line in a previous video, but what we didn't do in a previous video is figure out the equation of the secant line. And it turns out that'll be a useful skill several times in this class, so even though technically it's something you're supposed to learn in a pre-calc class, I want to review it in this video. There's at least two different ways to figure out the equation of a line when you already know the slope of the line and you know at least one point on the line. The first one is what's called point-slope form. And it's a form that's less commonly used by students, although what you'll see is it's pretty useful for this class. The idea with point-slope form is if you have a point that we call x1, y1, and you have the slope that we call m, then we can come up with the equation of the line by plugging into y minus y1 equals m times x minus x1. This form right here is what's called point-slope form. And I have written down in pink everything that I need to come up with the point-slope form of this specific line. Playing the role of the m should be the number 2, and playing the role of x1 and y1 should be 3 and negative 2 respectively. So instead of y minus y1, I have y minus negative 2, in other words, y plus 2. And instead of x minus x1, I have x minus 3. This is the point-slope form of the line given in pink. You could say you're done here because you've technically determined an equation of the secant line. This is an equation and it represents that line. Although typically, when it's not specified, most people don't think about point-slope form as the standard form of the equation of a line. They think about slope-intercept form as the standard form of the equation of a line. And I know that's a lot of vocabulary I'm throwing at you, but all I'm saying is typically people don't leave their answer like this. They instead solve this for y and get rid of the parentheses. And that's easy enough to do algebraically. To get rid of the parentheses, just distribute the 2 through the parentheses. So I would get y plus 2 is equal to 2x minus 6. And then to solve for y, subtract 2 from both sides of the equation, and I get y equals 2x minus 8. Well, I'm technically done here. I mentioned that there were at least 2 different ways to come up with the equation of this secant line. And I can tell you from experience that most students don't do it this point slope form way. Most students instead use what's called slope intercept form, which is what this final answer ended up being in, but they get there more directly. They don't go through point slope form. They say slope intercept form. In other words, y equals mx plus b is where I'm going to start. I'm not going to start with point slope form. I'm going to start with slope intercept form and plug directly into here. All I need to know slope intercept form is what number is playing the role of m and what number is playing the role of b. I already know what number is playing the role of m. I solved for that already. It's 2. So really my equation is y equals 2x plus b. If I just knew what b were equal to, I'd be done. Well, I can solve for b by taking either of these points, it doesn't matter which one, and plugging them into this equation. So maybe I'll take my first point. I'll say when y is equal to negative 2, the x is equal to positive 3, so negative 2 equals 2 times 3 plus b. What I now have is an equation with only one unknown, the letter b, so I can solve for that b. I got negative 2 is equal to 6 plus b. If I subtract 6 from both sides of the equation, I get b is equal to negative 8. I already knew m from over here in pink. Now I know b from over here in purple, so I can come up with my slope intercept form. I copy this first line, except I write 2 and negative 8 in place of m and b to get y equals 2x minus 8, the exact same answer that I got up here. I purposefully went really quick through all of this because it's supposed to be pre-calc review, but if you struggle with this, you might want to slow it down and try some examples on your own, because going forward, I'm going to assume that you can do all of this stuff. What I want to do a little bit more carefully is the stuff that's not pre-calculus, the stuff that's calculus. Pre-calculus, we learned a lot about secant lines. Calculus, we're interested in tangent lines. Remember, tangent lines are the ones that are more difficult because tangent lines are defined by one single point instead of 2 separate points like secant lines. So when I'm asked to find a tangent line over here, I'm expecting to only see 1 point. And sure enough, I'm only given 1 point, x equals 3. X equals 3 is this point that we've written a whole bunch of times. And if I want to sketch the tangent line, what I have to do is sketch a line that goes through this point so that the slope of that line matches the steepness of the curve in black at this point. For a lot of people, it's harder to say than it is to do. If you were picturing a line that kind of looks like this line in red for the tangent line to this curve at this point, that's fantastic. Sketching the tangent line to f at x equals 3 is just sketching this line that you see pictured in red. The problem with the tangent line as opposed to the secant line is we can't really calculate its slope at this point in the class because the line itself is kind of an estimate. The slope of that line is kind of an estimate also. But looking at this line in red, it looks like it goes up 1 unit each time it goes to the right 1 unit. Therefore, if I had to estimate the slope of this tangent line that's pictured in red, I'd estimate it to be equal to exactly 1. Something that I hinted at in a previous video but didn't actually do involves the fact that we can learn a lot about tangent lines by looking at secant lines when the 2 points that define the secant line get really, really close together. And we're going to actually do that down here. I think the slope of this tangent line pictured in red is 1. I mean, I did my best to draw this line, and this line has a slope of 1. Therefore, I think that the tangent line has a slope of 1, but there's a bit of a problem with that. I mean, we can't concretely construct this line in red. It's sort of a guess what it looks like. Tangent lines are hard, secant lines are easy. So let's take advantage of the fact that secant lines are easy to learn about that tangent line. Suppose you had a secant line where one of the points had an x-coordinate of 3, and therefore a y-coordinate of negative 2, and the other point had an x-coordinate of maybe, I don't know, 3.1. I could figure out the y-coordinate, and then using these 4 points, I could calculate the slope. Figuring out the y-coordinate is going to be a little bit annoying. We certainly can't use the graph, because figuring out the height corresponding with 3.1 would be a total estimate. But fortunately, we have the equation of the function 1/3 x squared minus x minus 2. So if we want to figure out the y-coordinate that corresponds with 3.1, really all we have to do is figure out what is f of 3.1. Well, that's just 1/3 of 3.1 squared minus 3.1 minus 2. What's that equal to? I don't know. I mean, I don't want to multiply 3.1 by 3.1 and then take 1/3 of that. So maybe I'll use Desmos. Desmos, if you don't know about it, it's a free site that has lots of good graphing capabilities, and it also has some calculators. I want to know 3.1 squared times 1/3, in other words, divided by 3, minus 3.1 minus 2. That's this number, which I can either leave as a decimal or convert to a fraction, depending on how precise I want to be. Negative 1.897. Now that I have 2 points, 3, negative 2, and 3.1, negative 1.897, I can calculate the slope. For the slope, I want to take this answer, y2, and subtract y1, so subtract negative 2. And then I want to divide that by the difference in the two x coordinates, so 3.1 minus 3. And what I get for my answer is 1.03 repeating. What did we just figure out? What we figured out is the secant line from 3 to 3.1. So picture a line in pink, except instead of the dots being this red dot and this pink dot, it's this red dot and a pink dot that's right next to it. That line would have a slope of 1.03. And maybe you're like, yeah, but 3.1 isn't really that close to 3. I mean, it's kind of close, but you can get a lot closer. Okay, so let's do one more iteration of this. What if it were 3.01? What if I took this second point and moved it even closer to 3? Well, what I'd want to do is come up here, and instead of doing 3.1 squared over 3, I'd want to do 3.01 squared over 3. And then instead of subtracting 3.1, I'd want to subtract 3.01. And what that would tell me is that the y coordinate that corresponds with 3.01 is negative 1.98996 repeating. Roughly negative 1.99. Using this point and this point, I can calculate the slope. What I have to do is take this answer and subtract negative 2. And then divide that by the difference in the x coordinates, so 3.01 minus 3. And what I get is 1.003. Can you see what's going on here? When my second x coordinate gets closer and closer to 3, my second y coordinate gets closer and closer to negative 2. Oh, that makes sense because I know that at 3, the y coordinate is negative 2. And when I use these points that get increasingly close to this point, the slope appears to be getting increasingly closer to 1. I'll leave it as an exercise to you, but I think if you plugged in 3.001, you'd get a y coordinate that's even closer to negative 2, maybe something like negative 1.999. And if you calculated the slope of the line with this point and this point, you'd get a value of m that's even closer to 1, maybe 1.0003. Maybe you start to see a pattern going on here. Maybe that pattern is enough to convince you that the slope of the tangent line, this line pictured in red, is in fact exactly equal to 1. Maybe secant lines are used as justification for this estimate of the slope of this line in red. We'll make that idea more concrete in future sections when we learn about things called limits, but we're not there yet, so for now this is kind of the best we can do. It's worth pointing out that now that we've confirmed the slope of the tangent line, there's no reason we couldn't find the equation of the tangent line. Just like we found the equation of the secant line up here, we could find the equation of the tangent line. Just like up here, there were 2 different options. Down here, there's 2 different options. I think what you'll find as the class goes on is generally point slope form will be more conducive to the situations that we see in our class. So I'm going to get you practice using this one. We start out with y minus y1 equals m times x minus x1, and we plug in. What do we plug in? Well, we've confirmed that the slope is equal to 1, so in place of m here, I'll write a 1. What values do we use for x1 and y1? Well, we need a point that is on the line. Which line? The tangent line. So don't use these points, which are on the secant line. We want to use this point in red, which is on the tangent line. We want to use x equals 3 and y equals negative 2. So I get y minus negative 2, in other words, y plus 2, equals 1 times x minus 3. This 1 really isn't doing anything at all. So I got y plus 2 equals x minus 3. If I subtract 2 from both sides, I get y equals x minus 5. This is the equation of the tangent line that we see pictured in red here. Oh, right, the slope is 1, and if I continued this line, it looks like it would intersect the y-axis right around negative 5. Last question for this video. Determine f prime of 3. It's not hard as long as you know what's being asked. The hard part is understanding what this question means. Remember, f prime of 3 is something that we saw a couple of videos ago. F prime of 3 represents the derivative of the function at the point where x equals 3. The derivative of the function represents the rate of change. This question here, determine f prime of 3, is asking you how steep is this curve at this point right here where x equals 3. Well, it's really hard to figure out how steep a curve is. Fortunately, it's pretty easy to figure out how steep a line is. The steepness of a line is just equal to its slope. And the nice thing about this tangent line is the way we created it in the first place is we drew a line whose steepness was the exact same at this point as the steepness of the curve. The way to think about it is, I'm asking you how steep is this curve at x equals 3? And you throw up your hands and you're like, I don't know. I can't measure the steepness of the curve. However, what I could do is sketch a tangent line. And the reason I'm going to sketch a tangent line is because I know the tangent line will have the same steepness as the curve at this point, and I can measure the steepness of the tangent line by calculating its slope. The slope of this line in red, as we've seen a few times, is exactly 1. Therefore, the steepness of the curve at this point is exactly 1. Therefore, f prime of 3 is equal to 1. If you understand how f prime of 3 is equal to 1 in the context of tangent lines, which we can confirm with secant lines, you've picked up everything that I need you to know in this video.